Here we're looking at some practice questions involving Kepler's third law. So up here we've got the first practice question. Use Earth's data to calculate Kepler's constant for the Sun. Then calculate the missing values for Saturn and for Venus. So you will recall that we have this equation, Kepler's constant is equal to the square of the orbital period divided by the cube of the orbital radius. So in order to use this, we can find Kepler's constant for the Sun using Earth's period and Earth's orbital radius. And then we can apply that over here. If we know the orbital radius of Venus, we can figure out its period. And if we know the orbital period of Saturn, then we can figure out its orbital radius. That K value is the same for the Sun. So let's start there. K Sun is equal to the period of Earth's orbit, all squared, over the orbital radius of Earth cubed. Now feel free to make smaller subscripts like KS and TE and RE. Just want to show all of this the first time. So K Sun is equal to, we'll grab here the orbital period of Earth, which I've already put into seconds for you. If it's in minutes or years, you would have to convert. And putting this into the calculator, we get K Sun is equal to 2.97 times 10 to the negative 19 seconds squared per meters cubed. This value holds true for the Sun. So anything that orbits the Sun will use this value for Kepler's constant. I'll let you guys try the data for Venus to figure out its orbital period and for Saturn to figure out its orbital radius. I'm going to start this next question off for you. So Galileo Galilei discovered Jupiter's 4 largest moons in the early 1600s, shortly after the invention of the telescope. Use Io and Europa's data to calculate and confirm the Kepler constant for Jupiter, then find the missing values for Ganymede and Callisto. So I included this question so that you could see that Jupiter's Kepler's constant is different from that of the Sun. So we're going to start with the K value for Jupiter. I'll just use KJ for that. And we'll look at Io's data. We're going to take the orbital period of Io, and that gets squared, and the orbital radius of Io, and that gets cubed. It's important to check that the units are the way that they should be in standard SI units, but I've already done that for you. So this is going to be 15285, whoops, there's a 5 there, 3 seconds. That whole thing gets squared, and then the radius gets cubed. 4.217 times 10 to the 8 meters, all cubed. So when you're punching this on your calculator, I recommend using the EXP button whenever you have something like this. 152,853, that gets squared, divided by 4.217 EXP8, and that gets cubed. So my suggestion here is that the Kepler constant for Jupiter is 3.11557 seconds squared per meters cubed. I forgot the exponent, times 10 to the negative 16 seconds squared per meters cubed. That's going to be very important, so you want to keep that. So in the next step, you would prove that by doing the same thing for Europa's data and checking that those two values are the same. And then you can use Jupiter's Kepler's constant to figure out the orbital period of Ganymede and the orbital radius of Callisto.